off basically with working with Python. So you're going to do an assignment, you've maybe seen it already, that solves a bunch of problems, tries to do it as efficiently as possible. And not only do you try and do it as efficiently as possible, but you analyze your solutions to explain how fast they run. So even if they're not that fast, you should be able to at least analyze them to say why they're not that fast. So the sort of things we've done in the last couple of classes. And so that's it then for assignments in Python. Next week we will start looking at Java, and we'll do an introduction to Java and a couple of assignments in Java, which, if you've been counting, that means you'll have done a total of 11 assignments, which is good because the class only asks for 10, so I'll take the best 10 out of 11 marks on those assignments and count those as your assignment mark. So if you really blew one, don't worry, you have a chance to completely make it up. Although even if you really blew one, there were still 9 others you could do to fix that, so it's not terrible anyway. All right. So one thing that you're supposed to learn in this course is you're supposed to learn about recursion, and we've been using it a bit already, but never really focused too hard on it. Because, well, one of the dangers with recursion is when you think too much about it, you can confuse yourself. So I've been trying to avoid that. I don't know. So early on in your so recursion by definition is when a function calls itself, or when it calls a function which calls another function which calls a function which then calls the original function back. So it's really defining, you can think of it as defining the solution to a problem in terms of itself. So it's sort of defining it in a cyclic way. And you have to be careful with that, because if you, when you define things in a cyclic way, well, you run into the danger of infinite loops, where a solution is defined in terms of another solution, which is defined in terms of another solution, which is defined in terms of another solution, which is then defined in terms of the original solution, and this would go on forever. So remember our friend the factorial function. I think it was from one of the first assignments, maybe the second one. So factorial is it takes an argument n, and it returns the returns n times n minus 1 times n minus 2 times n minus 3, and so on. So if we want to do that recursively, how do you define factorial of n in terms of itself? Or how do you find, more precisely, how do you define factorial of n in terms of factorial of something? Let's look at this formula. It says factorial of n is n times n minus 1 times n minus 2 times, and so on. So do you see a factorial in there? In this formula here, do you see another factorial? A smaller one, maybe? What about all this stuff here? What's that? n minus 1 times n minus 2 times n minus 3.
N minus 1 over and over again, but then just keep getting smaller.
Yeah, so what's another name for that? Yeah? Is this too easy for people? No. Right, if n factorial is n times n minus 1 times n minus 2 times n minus 3 and so on, then what's n minus 1 times n minus 2? Yeah?
The factorial of n minus 1.
Yeah. So this whole thing here is just the factorial of n minus 1. Right? It's just factorial with a different argument, n minus 1. And the good news is it's a smaller argument. Okay. So this says we should be able to solve this by the way we compute n factorial is we compute factorial of n minus 1 and then we multiply it by n. So is this going to work?
Yeah. But no. Stop it.
Yeah. So there's, again, recursion has these sort of two components. You want to define the solution in terms of solution to the same problem but maybe with a different argument. So we've got that done. To compute factorial of n, we need to compute factorial of n minus 1. But this is a cyclic now definition, and we need some way to break the cycle. And usually what happens in these things is you break the cycle by having an answer ready for the small values. And, well, if n is less than or equal to 1, then we'll just define n factorial as 1. So if it equals 1, then this definition defines it as 1. If it's less than 1, it's not clear what to do, but we'll just leave it at that.
That's not going to work.
Okay. That's not going to work? Why not?
It's going to end up just returning 1 in the end. It's not going to actually return a final factorial.
Well, let's see.
Well, it's going to, but it's just going to keep printing out more and more and more. We just want one answer. We don't want like 20 answers.
Okay. Well, let's see. Let's test it out and see what happens, and then try and understand why that happens. So let's try factorial of 1. That works. And why does that work? Well, that works because we check if n is less than or equal to 1, we return 1. Let's try factorial of 2. That works also. Factorial of 2 is 2 times 1. Factorial of 3? 6. That works too. So let's really dig into what's happening here. So when we call factorial of, let's say, let's go for 4, then what happens is we're calling a function, and so Python, the interpreter, sets up a little stack frame, a little environment for that function to execute in. And that function has one argument. It's called n. And so that environment has a variable called n, and it's already been assigned a value, 4. Then the function executes. It checks if n is less than or equal to 1. It's not. So it goes to the next line of code, which says return n times factorial of n minus 1. Well, now we're calling a function again. N is 4, so n minus 1 is 3. We're calling factorial of 3, which then Python sets up a little environment for and does this. Now, remember So what we're calling this function, and whatever value comes out of that, we're going to multiply it by n. So we call this thing, and whatever comes out of that, we're going to multiply by n. So let's just keep track of, after this returns, there's still a little bit of code to execute before we can return our value, and that's the code that multiplies this value by n. Well, factorial of 3 does the same thing. It checks if n is less than or equal to 1. It's not, so it calls factorial of 2. And we have to remember, I shouldn't say n here because we have a concrete value of n. We're going to multiply this one by 4. And we have to remember that whatever comes out of that, there's one more thing we do before we return it. We multiply it by 3. So factorial of 2 gets called with the value n equals 2. Checks if n is less than or equal to 1. It's not, so it calls factorial of n minus 1, which is 1. 1. That sets up this environment with n equals 1. And remember, factorial of 2, before it returns its value, it's going to multiply it by 2. And now finally, this one checks, is n less than or equal to 1? It is, so it's going to return 1. So this thing returns 1. And whatever gets returned, so this is done executing now, it's gone. And whatever gets returned by that gets multiplied by 2, because that's what factorial of 2 was just waiting for. It just needed this last value that's returned from factorial of 1 before multiplying it by 2. So it does that. So it returns 2 times 1. Factorial of 3 was just waiting for this return value, so it does that, and it returns, well, let's say this is 3 times 2 times 1 is 6. And then factorial of 4 was just waiting for that return value, and it returns 4 times 6 is 24. Okay. So each call to this function returns exactly one value, which is used by the function that called it, and is multiplied by n, except for the topmost call, the factorial of 4 call, which just returns the value to whoever was calling it. In this case, we were calling it just from the terminal. So is that clear what's happening there? Yes? No? Okay. So this is the way functions execute in just about every programming language. When you call a function, there's this whole little environment that gets set up just to hold the variables that are used in that function and the parameters to that function, and those get changed. And if that function itself calls another function, well, then another environment gets set up. So here we really call the factorial function 4 times, and at some point in time, there's actually 4 of these environments, all there, not executing, but all set up for each of those 4 calls. Okay. All right. So that seems to work. Let's try another one. So this is a really useless one because, especially in Python, we want to return x to the power n, but we want to do it using a recursive function, and we'll say that it only works for non-negative integer values of n. Okay. So x to the power of n, that's x times x times x times x times x n times. So it looks like this, x times x times x times x times x. And there's n there's n x's in that expression there. So how do we define that recursively? Yep.
Just make something equal 0, and then if that ends up equaling n, then stop, and then every time you're just returning x times x.
That sounds like a. I mean, that sounds like an iterative solution. So we want to define it in terms of. Well, we would like to do it some other way, maybe, that doesn't involve explicit looping, maybe, or so. Well, I mean, you can tell me what the code should look like, or you can tell me how you define x to the power n in terms of some other something to the power something. So what did we do with factorial? We looked at the definition, which was n times whatever, and we saw that we could pull out a big chunk of this definition, and just that was called factorial of something else. What about here? X times x times x times x times x n times. Is there a way to peel off something from that? And yeah.
We're going to return x times power x comma n minus 1.
Yeah.
And then define the power of x to the power of 1 of just the x.
Yeah. So what we want is the recursive call is going to look like x times power x n minus 1, right? Because all of these x's here, there's n minus 1 of them, which is exactly what it means. It's x to the power n minus 1. So this definition up here with n x's in it, well, that's just x times the same thing with n minus 1 x's in it. So there's our recursive flavor. Yep.
Don't you have to do an if statement for if it goes to 0?
Yeah, so we always have to have a base case. And so, well, we'll follow the documentation, which says that it only works for non-negative integer values of n. So what's our base case then? 0. So non-negative, the smallest thing that's non-negative is 0. So if n equals 0, what should we return? Return 1. So x to the power 0 is by definition 1, and so that'll work out, right? Because then x to the power 1 will be x times x to the power 0, which is x times 1. So let's try that. Two to the power 3, what's that? 8. 2 times 2 times 2 is 8. 2 to the power 4, 16. 5 is 32, so on. What about 2 to the power 5.5?
It's gonna round.
What will happen?
It's gonna stop after the first time.
It gets angry. Huh.
It's never gonna equal 0.
It says the maximum recursion depth exceeded in compare. And look at all that junk that it spit out. We'll maybe it's profile preferences. Let's go unlimited. So more than 512 lines came out of that. So why did that happen?
Because it went past 0.
Went past 0. So we called 2 to the 5.5, which then called, so power 2 5.5, called power 2 4.5, then 3.5, then 2.5, 1.5, 0.5, minus 0.5, minus 1.5, minus 1.6. It was never equal to 0, so this never returned. So maybe we'll just try and catch those kinds of errors. The answer is still wrong, or it'll return the wrong answer in those cases, but that's okay as long as we've specified that you shouldn't give us inputs that are not integer that way. Okay. So that'll fix that. Well, it won't really fix the problem because the problem is that somebody called our function with the wrong kind of argument, but it'll at least prevent this this sort of overflow from happening. Okay. So here's one. We want to, someone gives us an integer n, and we would like to return a string representation of that integer. So let's say we just want to use the usual decimal representation where it's expressed as a bunch of digits, and let's not even say non-negative, let's say positive. It's expressed as a bunch of digits, and those digits are 0 through 9. So, and let's say we want to, there's an easy way to do this. Of course, you just say string n, but that's not terribly exciting. So let's say, that we're building our programming language or our environment from scratch. We have no library functions to do these kinds of things. So we would like to have this work. So for example, we might have an input n, which is 1, 2, 5, 7, 9, 6. So can you see a way that we, using arithmetic operations, that we could maybe find out one of the digits of this number? So how would we get the last digit, the smallest one? Mod. Mod what? So somehow we want something to do with n mod 10. We'll just convert that to a string, although there's another way to do it, but I don't want to get into character encodings. So if I were just to return string of n mod 10, what is that? That's this digit right here, right? It's the last digit in my my integer. N mod 10 is the thing you get when you ignore anything that's a multiple of 10. Well, all of these things are multiples of 10. This is 90, this is 700, this is 5,000, 20,000, and 100,000. So, okay. Now how do I recurse? I've got one of my digits. What would I like to recurse on? Yep.
The same number with integer division of 10, formatting same thing.
Yeah. So I want to recurse on this part, which is just n divided by 10. This is n mod 10. So let's yeah. So format it int n divided by 10 should give me a string that represents this thing, and then I just want to stick the last digit on the end. Okay. So what's the base case here? How do we stop this from going on forever? Yeah.
The integer division is 0.
Okay, so
And divided by 5.
if n is 0,
If n divided by 10 equals 1.
okay, we could do that. Why? We could also say if n divided by 10 equals 0, then what would we return?
Whatever that.
Well, if n divided by 10 is 0, that just means that n is, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we'd still want to return something in that case, right? Well, let's see.
Return the first decimal point.
No, we just want to do, so this n is only supposed to be a positive integer, so that's all we have to worry about. So none, null. Let's try it. Let's try none, see what happens. Format int 20 gives 0. What's wrong here? It's close, right? What's happening? Yep.
On the final case where you put the int the if, you want to return the string representation of n instead of just a blank.
Yeah, which is really the same thing as the string representation of n mod 10. But now that we see that this is basically duplicating the code that's here, and this base case is just happening, so this will work, but so that works. But we can go back and streamline this code a bit. So it's really good to think hard about what your base cases are. And so this doesn't look right to me because we're basically doing the same work in these two lines of code. There's the same thing happening. So we think a little bit harder about our base cases, then really the base case is when n equals 0. And that's when we want to return nothing. If this only needs to work for positive integers, then we can return nothing in that case. Okay. So it seems to work. The only thing that it doesn't really work for is if I give it 0, it gives me back the empty string. But, according to the documentation, this only works for positive integers. That's clear how that works? So if we looked, for example, at this example here, the first thing we do is we extract this 6, and we put it aside, and then we recursively call on the number 1, 2, 5, 7, 9, which then extracts the 9 and puts it aside, and then recursively calls itself on the number 125, which extracts the 5 and the 7 and puts it aside. The 1, 2, 5, 7 extracts the 7 and then calls it itself on 125, which then calls itself on 12, which then calls itself on 1, which then calls itself on 0. Okay, and that's how that works. Now, what if we, so let's call this format int R. What if we don't want to restrict ourselves to positive integers? So we'd like negative numbers and we would like zeros. See any way to do that? So this is actually something that happens a lot in when you use recursion, is you have a nice recursive definition that works for most of the cases, or that you can use for most of the cases, but you need to first somehow precondition it, or make sure that, you know, if you're given one of these weird cases, you have to fix it so it fits into one of the standard cases. So for example, one of the problems is if n equals 0, well then we can, this format int R doesn't work. It just returns the empty string, but we can fix that and just have it return 0. What's another thing that doesn't work for this? What's that? If it's negative. If n is less than 0. How do we format those numbers?
Or negative, or just times it by negative 1.
Well, so let's see.
It returns.
So we're going to want to have a minus sign in our string, right? We want to put a minus sign in front of the number. And then we can do this recursive call to format which number? Can we have it format, what's that?
And mod 10. And mod, yeah.
Yeah, negative n. So the number is negative. If we negate it, it's now positive, which means that format int R can handle it. So we just want to put a minus sign in front of it, and then have a minus sign, and then format the positive version of that number. And so this is a pretty common sort of pattern with when you're using recursive methods. Is there's a real recursive method that does the real difficult work, and then there's a method that's the one people call that does the sort of the preconditioning, or the work that handle some side cases to make sure that the recursive method is ready to call. And sometimes here we do it to avoid calling the recursive method with bad arguments, but sometimes you also do it because the recursive method takes more arguments than you really want it to take. They're just used for keeping track of things. So maybe we'll see an example of that later. Okay, so we can try that. So now if we call format int 0, we get 0. We call it with a positive number. Forgot the regular call. So if it's not 0, it's not negative. That means it's positive, so we just call the regular recursive method. And it all works. Okay. So is that clear? Easy as pie. You could duplicate this. All right. How about this? A recursive version of the sum method in Python that adds up the elements in an array. How would we define that? Any ideas? Yep.
Return the first element plus the sum of all the other elements.
Okay, so return the first element plus the sum of all the other elements. So the recursive definition is return a at 0 plus the summer of a from 1 up to a length of a. That looks good. Right, so, and what's the base case? Yep.
If the len a equals 1, then return a at 0.
Okay, so if the length of a equals 1, return a at 0.
We'll just put round brackets around len a rather than square brackets.
Yeah, you're right. Does that look like it will work? Let's check it. A equals. So that's right, 15. Yeah, 2, 6, 4, and 3 adds up to 15. We can just check it, of course, against the built-in sum method. That works. Let's try a bigger example. So the built-in method says that. Our method says, oops, maximum recursion depth exceeded. Is there something wrong with our method? No, it's correct. What's the problem? What are we running up against? The length of A is 1,000 in this case. So if we start to draw one of these pictures, well, what we call is, summer of the original A, which has A is some array of length 1,000. That's no problem. That array lives off somewhere else. But then we call it on an array of length 999. So this has 1,000 elements. This now has 999. That calls it on an array of length 998. 998. And so on. And eventually Python says, look, I'm not going to let you make this many stack frames. And it actually tells you something along those lines. Maximum recursion depth exceeded, and gives you an error. So that's, mildly annoying, but it's a good lesson for us. It tells us that not only should we avoid infinite recursion, but we should avoid recursion that requires a very large depth. So infinite recursion is clearly bad because even if we had an infinite number of stack frames, it would run forever. But here, there's many environments, Python for example, that doesn't let us have an arbitrarily large recursion depth, and 10,000 or 1,000 is already above this limit. Do you see a way we could get around that for this function if we still wanted to do it recursively? Yeah.
Might be able to split it up into parts.
Yeah.
Sum each part and then add all this together at the end.
Yeah. So we'll have to be a little more careful. But here's one of them. Let's change our base case to 0. Now this isn't a great base case. because if A was an array of strings, now this isn't going to do exactly what we want, but let's say A only works, we only care about A's that contain numbers. So the idea is to break it up into parts and do recursion on the parts. So let's go with the simplest version of that and break it up into two parts. What sizes should those parts have? If you have to guess. So this isn't right. This code isn't finished yet, but if you have to break it up into two parts, what do you think is the right sizes of those parts? Half. Yeah. So we actually were breaking it up into parts before. We were breaking it up into a part of size 1 and a part of size n minus 1. That wasn't working out for us. So let's try breaking it up into half the elements. So we add up the first half of the array, 0 up to len of a over 2 minus 1, and then we add up the second half of the array, a of len over 2, a from len of a over 2 up to len of a minus 1. So remember, when you do this splicing, it includes the start index, doesn't include the final index. So that's why when you splice from a up to len of a, or 0 up to len of a, you get exactly the indices. So same way the range function goes from 0 up to n minus 1. So let's try that and see if it fixes the problem. No, really? I suspect we did something wrong here. Seems we need both base cases. Oh, so the problem here is we have a base case for length of a equals 0. We don't have one for length of a equals 1. And so if we look at what happens when the length of a is equal to 1, we split a into two parts. One part is of length 0, and the other part is of length 1. So it didn't get any smaller, so that's going to split it up into two parts. One of length 0, one of length 1. That's going to go on forever. So we actually need a second base case that handles the case when the length of the array is 1. There we go. So that seems to work now. Now, why does that work and the other one didn't? Well, to find that out, we can work through this stack issue. So we call first thing we do is we call summer of a on an array whose length is 1,000. So 1,000 is not 0 and it's not 1. So that then recursively calls summer of a twice. First thing it does is call summer of a on an array whose length is 500. So these are our stacks so far. We have one where the array is of length 1,000, one where the array is of length 500. Well, that calls it twice again. Once where the length of a is 250, and then another one where the length of a is 250, which calls it twice again. Once where the length of a is 125, and another where the length of A is 125. And this goes down for a while until eventually you have something like the length of A is equal to 2, which is still not 0 or 1. So it calls it on an array of length 1. And arrays of length 1, well, they actually know what to do. They don't make a recursive call. They just return the value of the one element there. So this returns. So far, all that's ever been on our stack is this path here. So first of all, how long is this thing? Yeah. So this is something like log base 2 of 1,000. And that is, it's about 10. 2 to the 10 is 1,024. So log base 2 of 1,000 is about 10. So that's the height of this stack here. And that's not bad, right? I mean, we're talking about a recursion depth of 10 versus the previous thing had a recursion depth of 1,000. Okay, so it gets all the way down there. And now this one, with an array of length 1, returns, and returns control back up to this, which has an array of length 2. So that's the first call. The left call is done now. And now it makes the right call. Now that's nice because this thing is off the stack already by now. And so this one makes its call, puts that something else back on the stack, but the stack doesn't really get any higher than it already was. And the same thing happens. This returns, which then allows this thing to return, and then its parent, the thing that called it, will make the same type of, it'll make its second recursive call, which will make its 2 recursive calls, and so on. And we get this nice picture, which we've seen before, which is what we call a binary tree. And if we look at the number of the things along the bottom here, well, each thing along the bottom is an array of length 1. Or sometimes an array of length 0, but that's not really that important. Each thing along the bottom is an array of length 1, so there'll be 1,000 of those. And, well, the height of this thing is going to be log base 2 of 1,000. So the number of elements on the recursion stack at any given time is only about 10, but it adds everything up without difficulty. So is that clear-ish? Now, let's think about this a little more carefully. So does this function now remind you of any function that we've done before? Not binary search. Yeah. Yeah, merge sort. So merge sort had this structure, right? It sorts the first half of the array and it sorts the second half of the array. It has base cases for when the array is of length 0 or 1. And, well, do we remember how long merge sort took? Not very. But just in terms of the number of operations, to compute that, we built one of these trees and we added everything up, right? And so we decided that actually at the root, what merge sort does is it merges 2 sorted arrays, and that takes of length, let's say, 1,000 if we're calling it on 1,000 elements. So it does 1,000 steps at the root of this thing, and then it has these 2 subproblems, each of which is of size 500. So it does 500 steps here, does another 500 steps here, and Therefore, it does 1,000 here. Then, at this level, there's 4 of them, each of size 250. Add all those up, you get another 1,000. And you get basically at each level, you get 1,000. So add all those together, and you get, well, log base 2 of n, which is 10 times 1,000, is equal to 10,000. And the same thing's happening here. We call these arrays on two sizes of each one is half the size. But to do that, we're basically making a copy of the first half of the elements and a copy of the second half of the elements. Now that takes time. So to copy half the elements, let's say 500 elements, takes 500 steps. And to copy these 500 elements takes 500 steps. So this really is the same kind of work, right? We copy 500 elements and another 500 elements, so that's 1,000 steps at the root. And then the same thing happens recursively. So this whole process of taking the sum of this array is taking about 10,000 steps for an array of length 1,000. Is that a good way of doing it? No, not really, right? There's an easier way to take the sum of an array of length 1,000 that only takes about 999 steps, right? You just iterate over the array and add up the numbers. You only have to do 999 additions to get that to work. So, is there any way to make this more efficient? So what takes all the time in this function? Splitting it up. This copying the elements here takes all the time. So we could actually do this a different way. So, or let's do it, let's try it this way. So we'll write a recursive helper function that's going to sum up the values in A, but it's only going to sum AI plus 1 up to AI plus n minus 1. So it's a more general function. Now the nice thing about this, so now the base cases are different. It's not the length of A we're interested in. It's n, if n is 0 or n is 1. So if n is 0, that means this sum is empty. If n is 1, it has one element in it, and that element is AI. And now the nice thing about this is let's see, I comma n divided by 2 a I plus n divided by 2 and minus n divided by 2. Yeah. So what's different about this function is we don't make any copies of elements in A anymore. So to add up AI plus 1, AI plus n minus 1, we add up the first half. That starts at AI and goes to AI plus n over 2 minus 1. And then we add up the second half, which starts at AI plus n over 2 and goes to AI plus n minus 1. So let's call this one summer 0. And then summer of A, just call summer of R at 0 and length of A. Okay. Now if we go back and analyze this, well, things change considerably. So how much work do we do at the root here? To sum an array of length 1000, or an array where the argument n is equal to 1000, we check if n equals 0, we check if n equals 1, and then we just call two methods recursively. There's not much work there, which means that this number that was 1000 before is now something like, I don't know, let's say 3. So it's just a constant amount of work. It doesn't depend on n anymore. And now the same thing happens here. We do 3 and 3. We get 6. And now the same thing happens here. We do 3, 3, 3, 3. We get 12. Until we get down to the bottom, where the amount of work that we do is about 3,000. So does anybody know what all this adds up to? Not really. So this adds up to about 6,000. And more generally, this ends up being 6 times the value of n, whereas over here this was log n times the value of n. So if we use really big n's, then we'll see a difference between the two, and we can try that. So we have summer 0, which is the original one, and this new one, summer, and it calls summer R, summer R. So both are extremely fast. So let's go with a bigger value of A. Let's go bigger still. Pretty close. Well, so if A gets bigger, I don't know if I can actually do that. This is going to be slow. We ran out of memory again. So if A were not, so if we could, if Python, this version of Python were not limited, we'd see that these two things start to diverge. One of them does this in about 6 times n operations, and the other one does it in log n times n operations. Well, log n keeps getting bigger and bigger, and it's bigger than 6 certainly, and so the 6 times n is the better way to do it. Okay, we'll finish with one that we'll come back to next class, and there's something similar on the assignment. Anybody know what Fibonacci numbers are? So they're actually defined recursively, right? So what's the 0th Fibonacci number? It's 1. So the story of these things is Fibonacci was interested in studying rabbits. And, so he observed that rabbits reproduce a lot. And So he said, well, you know, if I start with 2 rabbits, then how many rabbits will I have after n generations? So, or how many offspring will these things have? So, I forget the model exactly, but basically that one generation will reproduce, well, I don't know, with the next generation, let's say. And so this is the number of these things that I get. So it's really, Fibonacci numbers are defined recursively. Fibonacci of 1 is 1, 2 is 2, 3 is 3. So, and what's 4? Just so you got the definition. What's Fibonacci of 4? So it's Fibonacci of 3 plus Fibonacci of 2, which is 5. Fibonacci of 5 is 8. And how about Fibonacci of 1000?
Big.
Guess how big? We'll never know. How about even Fibonacci of 100?
Less good.
Again, we'll never know.
Unless you calculate it by yourself.
Well, unless you calculate it by yourself.
That.
So we should think, well, you don't want to calculate things by yourself. That's what computers are for. So next class we'll come back and see how we could get this number Fibonacci 100. Seems recursion isn't going to do it for us.